Alright, so let's say you're given this diagram here of a compressed spring moving from point x1 to x2, and the question says, find the work done by the spring when the mass is stretched from point x1 equal to -6 centimeters to point x2 equal to -2 centimeters, relative to the equilibrium position. To start, we know from last time that the elastic potential energy of a spring is given by this equation here, where k is the spring constant and x is the displacement between x1 and x2. From this definition, we can define the work done by a spring as this, where the first term is the elastic potential energy at point 1, and the second term is the same thing at point 2. So we could plug these in, and then we can identify the change in the elastic potential is equal to u2 minus u1. And if we multiply both sides by -1, we get the expression that's in our equation. So if we plug this in, we get this final equation here for the work done by the spring. This means that the work done by the elastic force of the spring is equal to the negative change in the elastic potential energy. We can apply this to our example. We have our 2 points x1 and x2, and if we remember, spring force is equal to k times x and is always pointing in the direction of the equilibrium position. Look at our diagram here. We can draw our spring force pointing towards the equilibrium position at x equals 0. Our displacement vector is going to be pointing from x1 to x2 like so. Since delta s is defined as our displacement vector from x1 to x2, note that general work equation is equal to force times displacement. For this spring force and displacement in our example, they're pointing in the same direction. If we look at our diagram here, they're both pointing toward the right, so our work should be positive. So if we use the equation we found for work, which is work equal to the negative change in elastic potential energy, and we rewrite it in this form, we can identify x1 equal to -6 centimeters, and then x2 is equal to -2 centimeters. Spring constant's equal to 15 newtons per meter. But if we look at our units here, we have to convert the x1 and x2 to meters like so. And then we can plug this in and we get this expression, compute the square of this term here, and then we can compute the square of this term on the other side. We can plug both these values in, noting that they do become positive because we're squaring it. And then we can compute the amplitudes in units of the term on the left and the term on the right. And then if we plug this in, we can do a simple subtraction and we get this final answer for the work. So this is the work done by the spring force between x1 and x2. This makes sense since the force of the spring is causing the mass to move towards the equilibrium position x equals 0 between our 2 points x1 and x2. And the elastic potential energy that was stored from the compression at x1 is converted into kinetic energy, resulting in the mass moving towards x2 equals -2 centimeters. And if we remember our work equation, it's equal to the potential energy at point 1 minus the potential energy at point 2. If we look at what we solved for here, we can identify this as the potential energy at point 1 and this at point 2. So from point 1 to point 2, we lose potential energy because it's converted into kinetic energy, causing the mass to move towards the equilibrium position. And this is the work that the spring is doing.